Bonding a stainless steel backsplash in a commercial kitchen involves several considerations. Firstly, gas lines should never be bonded to the electrical grounding system. Bonding metal to a gas line can create a hazardous electrical path if the gas line leaks. Secondly, regarding receptacles and cover plates, stainless steel cover plates that come into contact with the backsplash will provide sufficient bonding for electrical purposes. However, to further ensure proper grounding, ground clips should also be attached to the backsplash and connected to the grounding conductor. Ground clips are small metal clips designed to connect a non-conductive surface like stainless steel to a grounding conductor. They provide a low resistance path for electrical current to flow from the stainless steel surface to the grounding system. When installing the stainless steel backsplash, follow these steps. 1. Install the stainless steel backsplash, making sure it fits tightly against the wall. 2. Cut out the necessary openings for gas lines and receptacles. 3. Place ground clips around the perimeter of these openings and securely attach them to the backsplash. 4. Connect the ground clips to the grounding conductor using a screw or bolt to ensure a solid connection. 5. Install the gas lines and receptacles, confirming they are properly grounded according to code. And 6. Install the stainless steel cover plates over the receptacles. The benefits of properly bonding the stainless steel backsplash are numerous. It provides a low resistance path for electrical current to flow in the event of a fault, which minimizes the risk of electrical shock and fire hazards. Furthermore, proper bonding ensures compliance with electrical safety codes, protecting the building occupants and equipment. To elaborate on the purpose and methods of electrical bonding and grounding, let's consider the broader context of electrical safety. Electrical grounding and bonding are essential safety measures designed to protect individuals and equipment from electrical hazards. Grounding provides a path for fault current to flow back to the source, causing the circuit breaker to trip and energize the circuit. Bonding connects metallic parts to create a low impedance path for fault current, ensuring that all exposed metal parts are at the same electrical potential, thereby minimizing the risk of electric shock. The National Electrical Code, or NEC, provides comprehensive guidelines for grounding and bonding. It specifies the types of equipment that must be grounded, the methods of grounding, and the size and type of grounding conductors. Understanding and adhering to the NEC requirements is crucial for ensuring electrical safety. Grounding systems can be broadly classified into two types: firstly, equipment grounding, and secondly, system grounding. Equipment grounding connects non-current carrying metal parts of electrical equipment to ground, such as enclosures, raceways, and motor frames. System grounding, on the other hand, connects the neutral point of the electrical system to ground, which helps to stabilize the voltage and provide a path for fault current. The size of the grounding conductor is determined by the size of the overcurrent protection device in the circuit. The NEC provides tables that specify the minimum size of the grounding conductor based on the ampere rating of the circuit breaker or fuse. For example, NEC Table 250.122 specifies the minimum size of equipment grounding conductors for various circuit ratings. The grounding conductor must be made of copper or of a corrosion-resistant material and must be securely connected to the grounding electrode. The grounding electrode is typically a ground rod, ground plate, or metal water pipe that is buried in the earth. The grounding electrode provides a connection to the earth, which helps to dissipate fault current and maintain a stable ground potential. Bonding involves connecting metallic parts of electrical equipment and systems to create a low impedance path for fault current. This ensures that all exposed metal parts are at the same electrical potential, minimizing the risk of electric shock. Bonding can be achieved by using bonding jumpers, bonding screws, or other approved methods. The NEC requires bonding of metal raceways, metal enclosures, and other metal parts that are likely to become energized. The bonding conductor must be sized according to the size of the circuit conductors and must be securely connected to the metal parts. For example, NEC Section 250.96 specifies the requirements for bonding metal enclosures containing service conductors. In addition to equipment and system grounding, surge protection is another important aspect of electrical safety. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning, switching transients, or other disturbances. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. SPD are typically installed at the service entrance, but they can also be installed at the branch circuit level to provide additional protection. The selection and installation of SPD should be based on the recommendations of the manufacturer and the requirements of the NEC. Regular inspection and testing of grounding and bonding systems are essential for ensuring their effectiveness. Grounding and bonding connections should be checked for tightness and corrosion, and grounding conductors should be tested for continuity. Ground resistance measurements can also be taken to verify the effectiveness of the grounding system. Any deficiencies should be corrected promptly to maintain electrical safety. In commercial kitchens, special attention should be given to grounding and bonding due to the presence of water, metal equipment, and high electrical loads. All metal equipment, such as stainless steel tables, sinks, and cooking equipment, should be properly grounded to prevent electric shock hazards. Ground fault circuit interrupters, or GFCIs, should be installed in all receptacles that are located near water or in damp locations. GFCIs are designed to detect ground faults and interrupt the circuit, preventing electric shock. In addition to grounding and bonding, proper wiring practices are also essential for electrical safety. All wiring should be installed in accordance with the NEC and should be protected from physical damage. Conductors should be properly sized for the load they will carry, and connections should be made using approved methods. Overcrowding of conductors and junction boxes and panel boards should be avoided, as this can lead to overheating and fire hazards. Regular maintenance of electrical equipment is also important for preventing electrical hazards. Electrical equipment should be inspected regularly for signs of wear, damage, or overheating. Loose connections should be tightened, and damaged components should be replaced. Motors should be lubricated according to the manufacturer's recommendations, and ventilation openings should be kept clear to prevent overheating. Employees should be trained on electrical safety procedures and should be provided with appropriate personal protective equipment, or PPE, such as rubber gloves and safety glasses. Training should cover topics such as hazard recognition, lockout/tagout procedures, and the proper use of electrical test equipment. Lockout/tagout procedures are used to energize electrical equipment before it is worked on, preventing accidental energization and electric shock. In summary, proper bonding and grounding of stainless steel backsplashes, along with adherence to electrical safety codes and best practices, is critical in commercial kitchens. This includes understanding the specific requirements for gas lines, receptacles, and the use of ground clips. It is always recommended to consult with a qualified electrician to ensure that all electrical work is performed safely and in compliance with applicable codes and regulations. To further discuss the importance of ground fault circuit interrupters, or GFCIs, and arc fault circuit interrupters, or RFCIs, let's delve into their specific roles in enhancing electrical safety. GFCIs are designed to protect individuals from electric shock by monitoring the current flowing in a circuit. If a ground fault is detected, which is a leakage of current to ground, the GFCI will trip the circuit, interrupting the flow of electricity and preventing a potentially fatal shock. GFCIs are particularly important in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. The NEC requires the use of GFCIs in these areas to protect people from electric shock hazards. GFCIs work by comparing the current flowing in the hot conductor with the current flowing in the neutral conductor. Under normal conditions, these currents should be equal. However, if a ground fault occurs, some of the current will leak to ground, causing an imbalance between the hot and neutral currents. The GFCI detects this imbalance and trips the circuit, typically within a fraction of a second. RFCIs, on the other hand, are designed to protect against fires caused by arcing faults. Arcing faults occur when electricity jumps between two conductors, creating a high-temperature arc that can ignite nearby combustible materials. RFCIs are particularly important in bedrooms and other areas where there is a high risk of fire. The NEC requires the use of RFCIs in these areas to protect against fire hazards. SIs work by monitoring the current flowing in a circuit for the characteristic signatures of arcing faults. These signatures include rapid changes in current and voltage, as well as high-frequency noise. When an arcing fault is detected, the SI trips the circuit, interrupting the flow of electricity and preventing a fire. There are two main types of SIs: firstly, branch/feeder SIs, and secondly, outlet branch circuit SIs. Branch/feeder SIs are installed in the panel board and protect the entire branch circuit. Outlet branch circuit SIs are installed in the outlet box and protect only the portion of the branch circuit downstream from the outlet. The selection of the appropriate type of SI depends on the specific application and the requirements of the NEC. In addition to GSEIs and SIs, surge-protected devices, or SPDs, are also important for protecting electrical equipment from voltage surges. Voltage surges can be caused by lightning, switching transients, or other disturbances and can damage sensitive electronic equipment. SPD divert the surge current to ground, preventing it from reaching the equipment. SPD are typically installed at the service entrance, but they can also be installed at the branch circuit level to provide additional protection. The selection and installation of SPD should be based on the recommendations of the manufacturer and the requirements of the NEC. Proper coordination of overcurrent protective devices, such as circuit breakers and fuses, is also essential for electrical safety. Overcurrent protective devices are designed to protect electrical circuits from overloads and short circuits. When an overcurrent occurs, the protective device will trip the circuit, interrupting the flow of electricity and preventing damage to the equipment and wiring. The coordination of overcurrent protective devices involves selecting devices that will trip in a coordinated manner, so that the device closest to the fault will trip first, minimizing the extent of the outage. The NEC provides guidelines for coordinating overcurrent protective devices to ensure proper protection of electrical circuits. Regular inspection and testing of electrical equipment is also important for preventing electrical hazards. Electrical equipment should be inspected regularly for signs of wear, damage, or overheating. Loose connections should be tightened, and damaged components should be replaced. Motors should be lubricated according to the manufacturer's recommendations, and ventilation openings should be kept clear to prevent overheating. Employees should be trained on electrical safety procedures and should be provided with appropriate personal protective equipment, or PPE, such as rubber gloves and safety glasses. Training should cover topics such as hazard recognition, lockout/tagout procedures, and the proper use of electrical test equipment. Lockout/tagout procedures are used to energize electrical equipment before it is worked on, preventing accidental energization and electric shock. Electrical safety is a critical aspect of workplace safety and should be given the highest priority. By following the guidelines and requirements of the NEC and by implementing appropriate safety measures, employers can protect their employees from electrical hazards and create a safe working environment. In the context of commercial kitchens, the presence of stainless steel equipment, water, and high electrical loads necessitates a thorough understanding of electrical safety principles. The information provided serves as a general guide, and it is essential to consult with a qualified electrician for specific applications and to ensure compliance with all applicable codes and regulations. Remember, safety is paramount, and taking the necessary precautions can prevent accidents and save lives.